evening, everyone. Welcome to my series, Best Helping Hand in Jump. We started talking about equilibrium in the last class. I discussed what's the definition of equilibrium and when is a body said to be in equilibrium, and we gave the types of equilibrium based on whether it is static equilibrium based on their virtue or dynamic equilibrium. Then we also define it's based on stability of a body. We talked about stable equilibrium, unstable equilibrium. In this video, we are going to see how we interpret a question when you are given a question. So sit back, relax, and please, if you have not subscribed to my YouTube channel, please do so by clicking on the red button to subscribe. Also click on the notification bell to be notified. So our question used to be set in this particular question is either you are given the first type of question you can have is a lever, or some people may pronounce it as lever. Let me say one lever. When you have, what I mean by lever, when I have a beam and I have a fulcrum. So when you're applying point load is represented by arrow. Point load means a load that is being applied at a point. So this is a lever. We have a fulcrum here, which serves as our reaction or our pivot. Then we can have a load at this place. We can also have something like an effort at this place. It doesn't really matter. It may not be load or effort. It may be a combination like this of forces. Just because it has only one reaction, it is referred to as lever. This is referred to as lever. To solve a problem on lever, to find the reaction of a lever, it is very simple. You can only say sum of upward force, which is this R, reaction at this place, RA. Sum of upward force is equals to sum of downward forces. So if we have this one to be called P1, this is P2, this is P3. So we can say that our reaction at A, at point A, reaction at A is equals to P1 plus P2 plus P3. If you remember the principle of equilibrium, we say what? Our sum of what? Upward forces must be equals to sum of downward forces. Sum of downward forces. So that is case one when we are dealing with lever. But when we are dealing with another one we can have is simple support. And I reinterpret the meaning of this simple support. This simple support is when we have two fulcrum. When we have two pivots, we call it simple support. So the pivot at A, we give a reaction, normal reaction at A. It will be pushing it like this upward. So this is represented by reaction at A, while the pivot at B shows it moving upward at B. I believe you don't have any problem with that. So then let's look at this. In this case, we are looking at some ways that point load can be. The ways we can have point load. Point load can be in a direction like this. It can be written downward. For example, in the case of weight, point load can be other things apart from weight. It can be like a mass that is being hung. When you hang a mass, point load can be like this. So we represent point load by arrow pointing at a particular point. So if we have the next one we are going to consider is called cantilever. Cantilever is another type of problem. In this cantilever, there is no support, no fulcrum at all. Look at this lever has one fulcrum or one support. This simple support has two supports. But this cantilever doesn't have any support, rather it has load. It has load on it. It also has load on it and is supporting it. Example of cantilever are those boards that when you've gone to swim, you will walk on that board and you will bounce on it, then before you jump into the swimming pool. It's an example of cantilever. there is nothing supporting at the under. It is only supported at the edge. This is referred to as cantilever. So in the case of cantilever, when you want to resolve cantilever, a cantilever, in this case cantilever. So this is what we use to show cantilever. So we can have numerous point load on it. Point load is what you only know for your level. We still have other types of load. We have uniformly distributed load, we have gradually increasing load, we have non-uniformly distributed load. So you don't need to worry yourself. When you studying engineering, in your strength of material, you come across them. But let's just do the little physics that you need to know in this. So this is called cantilever. So what is the logic behind this cantilever? This cantilever, there is a reaction at this place that is acting upward. This reaction helps to overcome all this downward point load. So the upward point load here will be equals to sum of all these downward point load. So that is one thing about this cantilever. The second thing about this cantilever, what prevents it from falling down is there is another force that is acting in this direction. Another force is acting it in this direction, holding it firmly to the wall. Another is holding it firmly to the wall. So that is why it's not falling. One is acting upward, the other one is acting horizontally and entering into the wall or wherever they fixed the cantilever. So we have seen that. So we have reaction here. So and we can take this as our reaction B. So reaction A, reaction B. So but let's just leave it at this point. Another type of load you can have is in the case of this case 3. So we have case 1 here, cantilever. We have case 2. This is case 1, lever. Case 2, cantilever. Case 1, we have lever or simple support, which I have explained here. Case 2, we have cantilever. And case 3, we have a fulcrum here or a support here, and we also have a tension. When you use a rope to tie this beam, at this point you use a rope to tie it to the wall, making a particular angle with the horizontal. Sometimes they may give you to you making angle with the vertical. There is no problem. Please pay attention, because at this point you need to really learn this. Case 3. So in this case 3, when we have a support at this point, then we have a point here, a tension here, making angle theta with the horizontal. So in one of the previous video, I explained to us that any vector that is acting in inclined is useless, so you have to revert into vertical component and horizontal component. So you resolve this into vertical coming from that point where it leaves the beam. So I'll resolve into vertical component and horizontal component. So the vertical component is moving upward in this direction, horizontal component is moving in this direction. So if this is theta, this is also theta. Why? We have what is called alternate angles are equal. Hence, this vertical component will be T sine theta. T sine theta. So we have this tension in this string to be drawn upward like this. We have a reaction which will be drawn upward and tension drawn upward. So you can also have some other point load on this beam, so that they will give you a question or ask you to find a particular thing. So I hope you enjoyed this class. Please, if you have not subscribed to my channel, please do so. I believe that this class is going to be very helpful in your JAMB. Thank you. We move to the next one. Solving of problem. Examples. Solving of example that involves equilibrium. Solving of example that involves equilibrium. Question number 1. We have a lever. We have a pivot at this point, F1 and F2. Find the ratio of distance A to distance B. If FA ratio F1 ratio F2 is equal to 1:2. So this is very simple. Solution. So this is very simple. So remember that at the reaction, upward force must be equal to downward force. So that is that. So this is the reaction. So I'll call that reaction R. So the point load I have here, I will draw it here, and the point load I have here, I will draw it here. So F1, and here is F2. So then the distance here is A, then the distance here is B. So find A ratio B. So how do we find? We take moment about R, taking moment about R. So when we take moment about R, what happens? R, let's assume this point is R. F1 is pushing downward, which makes it clockwise direction. So this is clockwise moment. Why this F2 is clockwise moment? Let's look at the moment of F1 about R. So anti-clockwise moment. This is anti-clockwise moment. So taking moment about R, we have seen that sum of clockwise moment equals to anti-clockwise. So I have F2 multiplied by B clockwise moment must be equals to F1 multiplied by A. So which is sum of clockwise moment about R. Sum, let me use sum of clockwise moment about R is equals to sum of anti-clockwise moment about R. So let's not forget that is the principle of equilibrium. So hence I have yes, so now I have F1 ratio F2. So I have B over A is equals to F1 all over F2, which is equals to 1/2. So now to find A ratio B, so which implies that A over B will be equals to 2/1. Hence I have A ratio B to be equals to 2/1. So that is that. Question 1 solved. Question 2. Question 1. Question 2. To find X. So here we now have also a lever where we have a reaction at this point. We have point load here, point load here, and point load here. So we take moment about this reaction. Taking moment about this reaction, taking moment about R. So this is our R. So sum of likewise, this is anti-clockwise. So sum of clockwise moment, this is clockwise. So sum of clockwise moment must be equal to sum of anti-clockwise moment. So clockwise moment, I have 2 multiplied by 32.5. 2 multiplied by 32.5 must be equals to 20 times x plus 15 multiplied by the distance. 15 multiplied by 2 plus x. So when we multiply this, we have what? 65 is equals to what? 20x plus 30 plus 15x. So we'll bring 30 here, so I have 65 minus 30 is equals to 35x. So 35 is equals to 35x, hence x is equals to 1 when you divide both sides by 35. So we have been able to see how we use the sum of clockwise moment equals to sum of anti-clockwise moment to find the distance here. So we move to example 3. Example 3. Okay. Example 3. So let me pick from this. Our example 3. Example 3. I have still a lever, tension at this point, and point load at this point. So you can pause the video for you to see if you can solve it. This is 0. Here is at point 30, since it's a meter rule. Here is point 50, here is point 80, and here is 100, since it's a meter rule. So how can we go about this? Very simple. We're given the angle it's made with the horizontal to be 60 degrees. So very simple. Step number 1, resolve this this tension, resolve it into vertical component and horizontal component. So vertical component here will be equals to the T tension sine 30. The distance. So then let's now look at which of them is clockwise, which of them is anti-clockwise. Sum of clockwise must be equals to sum of anti-clockwise, taking moment about r. So taking moment about r, So taking moment about r makes it very simple. We now have the distance between here and here is 20. So we have this is anti-clockwise moment, while this is clockwise moment. So here I have 1.5 kg. So that is 15 Newton if acceleration due to gravity is. So I have taking moment about r. So I have sum of clockwise moment. Clockwise is 15 Newton multiplied by the distance. The distance is 15. Is equals to sum of anti-clockwise moment, which is equals to T sine 30 multiplied by the distance. Distance is 20 times 20. So this times this is what? Or better still, so I have T to be equals to sine 30 is 1.5. 1.5 multiplied by this 10 is equals to 10 multiplied by 50. So divide both sides by 10. So I have T to be equals to 10 multiplied by 5 and 25. That is 75. So tension is 75 Newton. So question number 4. Pause the video and see if you can solve question number 4 by yourself without any assistance. So solving question number 4. So question number 4 is not a lever like question 1, 2, 3. Question number 4 is simple supported system. That's question 4. Is a simple support system, and we are asked to find the reaction. We are asked to find the reaction at the two supports. To find the reaction at the two supports. So there is 4 Newton. I have here to be 10 Newton. Here I have it to be 7 Newton on a meter rule. So distance here I have it at 5. Here I have it to be 25. While this one is at 45. Here is at 80. Here is at 90. So how can we find this? This is very simple. So we call the reaction here RA. We also call reaction here RB. Remember, sum of upward forces must be equal to sum of downward forces. So it means upward forces are RA plus RB must be equal to sum of downward, which is equal to 4 plus 10 plus 7. So which is equal to 21 Newton. So then taking moment about RA. Taking moment about RA. Your daddy, that's my girl. Taking moment about RA. So how do we solve for RA? When we take moment about RA, we say sum of clockwise moment is equal to sum of anti-clockwise moment. So let's identify those that are clockwise and those that are not clockwise. So this is anti-clockwise. So we are talking about RA, so we don't need to take moment about it because it's already 0 about that point. So this is clockwise, this is anti-clockwise, and this is clockwise. So sum of clockwise moment is equal to sum of anti-clockwise moment. So I have clockwise moment 10 multiplied by the distance between it, that is 20, plus another clockwise, which is 7 multiplied by the distance between them, which is 65 times 65 is equals to 4 anti-clockwise multiplied by the distance between them, 20, plus another anti-clockwise is RB, times the distance between this and this is 55. So we can multiply them and then get the final answer. We see that this times this will give us 200, this times this will give us 455, then this times this will give us 80, then we have 55 RB. So collection of like terms, we have 55 RB to be equals to 575. So we divide both sides by, to get our RB, we say our RB is equals to 575 575 all over 55, which is equal to 10.455, which is equal to 10.45 Newton. So remember that we say our RA plus RB must be equals to what? Sum of all those vectors, the sum of all those forces, which is equal to 21 Newton. 21 Newton. So hence our RA will now be equals to 21 minus RB, 10.45. So which is equals to 10.55. So you have 21 minus 10.45. So we have 10.55 Newton. 10.55 Newton. So please, if you have not watched my video on how to know a clockwise moment and anti-clockwise moment, please, you can go back and check those videos where I've once explained how do you know a moment is clockwise and how do you know a moment is anti-clockwise. Please subscribe. It costs you nothing. It costs you nothing, not even data, for you to just click on the red button. Please help the ministry and encourage us in doing this good work by subscribing to our channel. So thank you. God bless you. See you in the next video. Thank you.